3, 2, 1. Hey everybody, welcome back. This week we are talking about balancing chemical equations and predicting the products of a chemical reaction. For this lesson, our focus is going to be on balancing. Then there will be a second lesson where we go over predicting products. If you don't already have the following objects, pause the video and get the balancing equations worksheet, a writing utensil, and something I keep forgetting to mention, your chemistry notebook. Somebody sent me an email a few weeks back asking what needs to go in your notebook. Basically everything that is on Canvas, if you are printing these out, please make sure that you are putting them in your notebook after you turn them in, so that way they are in one spot and you can reference back to them if need be. So the objectives for today's lesson are pretty straightforward. We want to be able to balance a chemical equation by counting the number of atoms on both the reactant and the product side. In order to be successful for this lesson, you need to make sure that you know how to write the chemical formulas of ionic and covalent compounds. So remember that with ionic compounds, you use the cross and drop method, and with covalent compounds, you just look at the prefix and write that number in based off the prefix. In addition, you need to know how to write out the chemical reactions, so those skeletal equations, using correct symbols and formulas. This is what we went over in week 3. Last week in the discussion post, I asked you what the total mass of the reactants would be based off a given mass of the product. This idea is based off of the law of conservation of mass, which states that the matter cannot be created nor destroyed, only transferred. And this was discovered in the late 18th century by a French scientist by the name of Antoine Lavoisier. And, I'm throwing this in there because a lot of you are taking AP World History and you have your exam coming up, so just a little historical chemistry. And Lavoisier discovered that when he burned a piece of coal, if he trapped it so that the gas would not escape, the mass would never change. The coal was simply transformed into a different state of matter. So he started with 100 grams and he ended with 100 grams. It never changed. Here is another example using methane gas. In the lab this past week, one of the videos you were supposed to watch was for this chemical reaction, where we take methane gas and light it on fire and we produce carbon dioxide gas and water vapor. We know that this is a balanced equation because if you look on the left side of the arrows, so over here, we see that we have 1 carbon atom, we have 4 hydrogen atoms, and we have 4 oxygen atoms because this 2 coefficient distributes and multiplies by that subscript. Then if we look on the right side of the arrow at our 2 products, once again, we see that we have 1 carbon atom. I'm going to stay in order and look at hydrogen, and we have 4 hydrogens because the same deal, this 2 coefficient translates and multiplies by that 2 subscript. So we have 4 hydrogen atoms, and we have 2 oxygen atoms because this 2 coefficient multiplies over there. Alternatively, if we were to calculate the mass of that, we would find that 1 methane molecule has a mass of 16 grams, and 1 carbon dioxide molecule has a mass of 44 grams. The 2 oxygen molecules have a total mass of 64 grams. And the 2 water molecules over here have a total mass of 36 grams. If we were to add that up on each side, you would see that you end up with 80 grams for your reactants, as well as 80 grams for the products. If you're interested in learning more about how to calculate the mass of products, which we're going to be doing in a couple of weeks anyways, I will be posting an extension video. It's not required yet, but it's great to get ahead if you're able to and you want to. It's especially important if you're going to be taking AP chemistry next year. So Lavoisier's discovery of the conservation of mass is what has now led us to this idea of balanced equations. So he's pretty significant, but apparently the French didn't think so because they executed him by guillotine during the French Revolution. So if the total mass of the reactants and the products are not equal, something's wrong and something's not balanced. It cannot exist in nature. So let's take a look at this example. Go ahead and pause the video and see if you can determine the mass of silver on your own. When you think you've got it, hit play to check your answer. Did you get it? Hopefully you saw that the total mass of the reactants added up to 233.42 grams, which means that the total mass of the products also has to equal 233.42 grams. So in other words, if you have 125.55 grams of copper nitrate plus the mass of silver, that has to equal 233.42. Sorry, I'm writing this out. So if I were to write this out, I can do my unknown mass and set that equal to my total mass. So I can then work backwards and solve for my unknown mass of silver. And when I do that, I end up with the mass of silver being 107.87 grams, which is the mass found on the periodic table. So we are correct. Just to recap, matter cannot be created or destroyed, only transferred. This means that in addition to the masses being equal on both sides of the reaction, the number of atoms for each element also have to be equal. So what that means is if I have 7 oxygen atoms on the left side of the arrow, then I have to have a total of 7 oxygen atoms on the right as well. Here's another example. If I have 12 hydrogen atoms on the left side of the arrow, then I have to have a total of, you guessed it, 12 hydrogen atoms on the right. If I have a total of 5 aluminum atoms on the right side of the arrow, then that means that I have to have a total of 5 aluminum atoms on the left. Are you guys seeing the main picture here? If the atoms are not equal on both sides, then you need to add coefficients in front of the compounds until they're balanced. But when you are balancing equations, only add the coefficients. Those are the big numbers in front of the compound. I'm going to say this 3 times very slowly because it is very important. Never, ever, ever add or change the subscripts. That was once. I'm going to say it again. Never, ever, ever add or change the subscripts. I'm going to say that one more time. Make sure that you do not ever change the subscripts. The subscripts never change. So there we go, 4 times. To get started in balancing, the first thing you want to do is count the number of atoms on each side of the arrow. If you notice they're not balanced, then you can begin adding coefficients, not the subscripts, to try to balance it out. And then you want to just keep updating your count on each side of the arrow and keep adding coefficients only until everything is balanced out. But the most important rule and trick with balancing equations is that you need to be patient. This is a trial and error process. There is no set formula or secret. It's all about just trying different coefficients and seeing if they work and balancing, and if they don't, then erasing those and trying something new until it all balances and comes together. Before we begin, I'm just going to really quickly review a coefficient versus a subscript just to make sure that you never, ever, ever change the subscript. Only change the coefficient. For instance, if you have 3 H2Os, This 3 is a coefficient. We can change that. It's okay. We can change it so that it balances. The small number within a compound, this 2, is a subscript. That 2 will never, ever, ever change. We can have 1 H2O, we can have 6 H2O, we can have 3 H2O, but the point is, it is still always H2O. We never change the subscripts. So for example, 1 molecule of H2O, that means that we would have a 1 subscript of H2O. And normally if it's a 1, we just don't put anything. That means that there's 2 hydrogen atoms and 1 oxygen atom because these coefficients can distribute. Alternatively, if we have 3 molecules of H2O, once again, that 3 distributes. So we end up with 6 hydrogen atoms and 3 oxygen atoms. So just a helpful hint when we're counting so that you know how to count. The coefficients can tell us 2 things. The first one is the number of particles. Remember from week 3, we learned that there are 3 ways we identify particles depending on if it's an ionic compound, molecular compound, or single element. In this example, the coefficients tell us that we have 4 atoms of iron, 3 molecules of oxygen, and 2 units of iron 3 oxide. Also, on a different note, hopefully you recognize this as a synthesis reaction because we have 2 single elements, iron and oxygen, combining to make 1 compound. The second thing a coefficient can tell us is the number of moles. This is actually a unit that we use in chemistry. So the mole connects mass, particles, volume. They're all connected through this unit known as the mole. So it's a lot easier to remember because everything is basically a mole. So in this example, we have 4 moles of iron, 3 moles of oxygen, and 2 moles of iron 3 oxide. As a matter of fact, the mole is so important that we actually celebrate Mole Day in October. Very exciting. It's October 23rd, in case you were wondering. We use moles to determine the relationship between all these different compounds as well. And we call this the mole to mole ratio. And what that means is that for every 3 moles of oxygen, for example, there are 2 moles of iron 3 oxide, making that a 3-to-2 ratio. Or for every 4 moles of iron, there's 3 moles of oxygen, making it a 4-to-3 ratio. And we're going to keep doing a lot of practice with that mole to mole ratio. In order to begin practicing balancing, I'm going to show you what a balanced equation looks like and how I count the atoms. Then I'm going to do one problem to show you and then have you try the second problem on your own. The first step whenever you're balancing is to count the number of atoms on each side. So these are like the number of each element that occur. Then I write down each element. And what I like to do is I draw a line across here. And so I split it up into reactants and products, and then I begin counting the atoms on each side. For example, in this reaction, I have 1 carbon atom. I have 4 hydrogens. And once again, this 2 distributes, and I have 4 oxygens. I'm going to do the same thing over here. I'm going to rush through this actually, because as I'm writing, I'm realizing it's the exact same problem that I gave you guys earlier. Sorry about that. So what we are going to do is, if you look, we know that it's balanced because carbon and carbon are equal. Check, check. Hydrogen, hydrogen, both are 4. So check, check. And oxygen, oxygen, both 4. Once we've checked off all of those, then we can move on. If 2 out of 3 were balanced, it's not good enough. We need to go back and check our coefficients. So in this case, looking at our mole to mole ratio, we could see that for every 2 moles of oxygen, for instance, makes 1 mole of carbon dioxide. every 1 mole of methane requires 2 moles of oxygen. So this is just when we use these coefficients to tell us the mole to mole ratio. That's just really fun to say. I'm going to say that a lot. Let's take a look at this first practice problem together. Since it's already written out right here, I don't need to write out the skeleton equation. So in this case, I'm just going to jump straight into splitting it and counting my atoms and begin. So in this case, I have sodium and I have chlorine. And if I were to count my atoms on both sides, I see that I currently have 1 sodium atom and 2 chlorines. On the right side for my products, I have 1 sodium atom and 1 chlorine atom. That means that they're not balanced. Sodium may be balanced, but chlorine is not. And since chlorine has 2 on the reactants and only 1 here, I'm going to add a 2 coefficient and see if that works. When I do that, I need to update both of these. So now I have 2 sodiums and I have 2 chlorines. Well, now my chlorines are balanced, but my sodium is not. And that tends to happen. So once again, we're just trial and error trying to get everything balanced and equal. Since I have 2 sodiums now on the right, I'm going to put a 2 coefficient on the left, which changes this to 2. And look, now it's balanced. 2 and 2, 2 and 2. So now it's great. And the question is asking me, what is the mole to mole ratio between sodium and chlorine? So that's between sodium right here and the chlorine gas here. Remember that if there is no coefficient, that it's basically a 1. We don't write in the 1s for chemistry, but it's basically 1 right here. So that means that the ratio between sodium and chlorine is 2 to 1. For every 2 moles of sodium, we require 1 mole of chlorine gas. Let's take a look at the second example. Go ahead and pause this video and try to balance this on your own. Then hit play to check your work. I'm going to get started in 3, 2, 1. Did you get it? Let's find out. So once again, my equation's already written out for me, which is great. So all I need to do is balance. So once again, I'm going to split this up into the reactants and the products. I've got aluminum here and oxygen. I have 1 aluminum and I have 2 oxygen atoms. On the right side, it's going to be fun. I have 2 aluminum atoms and I have 3 oxygen atoms. Well, I'm a fan of going with the simpler route first and seeing if it works out on its own. So let's look at aluminum. I can add 2 here, but that may not necessarily work. So I've got 2 here, but now oxygens are still not balanced. Aluminums are, but oxygen is not. So what can I do to balance it? When you're stuck between something like 2 and 3, the best thing to do is think about what number they both have in common. So in this case, they both have 6 in common. So if we were to make this so that we have 6 oxygen, we can add a 2 here and a 3 here. That makes the oxygens balanced, but now we need to update our aluminum count as well. Now we have 4 aluminums and once again 6 oxygen atoms. So we have 4 aluminums. So what I need to do is now I need to go back and I need to update my aluminum for my reactants. So I'm going to erase this and I'm going to put 4 aluminum there. And I did that so that you can see that it's a trial and error process. There is no set way to balance. We just need to keep on adjusting. This is especially important to use a pencil. If you're doing balancing equations in pen, it's going to get really messy. It's going to be really hard to follow, and I may not give you credit if I can't read it. Please use a pencil so that you can erase and adjust as needed. Now let's answer the following questions. What is the mole-to-mole ratio between aluminum and aluminum oxide? So we have aluminum here and aluminum oxide. Once again, I'm looking at these coefficients. So I see that aluminum is 4 moles and aluminum oxide is 2 moles, which tells me that for every 4 moles of aluminum, we produce 2 moles of aluminum oxide. Similar question, what is the mole-to-mole ratio between aluminum and oxygen? So once again, here's aluminum, here's oxygen. This is 4 and 3, which means my answer would be a 4-to-3 ratio. Let's say that as you were doing this, you accidentally overbalanced it, so you got this equation instead. Technically, it's balanced, but we always want it to be as simple as possible. Remember, the coefficients should always be the simplest whole number. If all the coefficients are divisible by each other, we need to reduce them until they're no longer divisible. So in this case, these are all divisible by 2. So if I were to divide this all by 2, I end up with the simplest whole numbers down here. And this would be my correct answer. I know that this is correct because they are not divisible by each other. 4 is not divisible by 3, 3 is not divisible by 2 to get a whole number. Let's do the third practice problem. Oh, it looks a lot more complicated, but that's only because I added this polyatomic ion chart. Notice how in this problem, it does not give you the skeleton equation already written out. So the first thing we need to do before we can balance it is to write out that basic equation. Then we can go back in and count the atoms and balance it. At this point, you should already be proficient in writing equations. So I'm going to go through that part pretty quickly. If you're still not sure about writing out basic skeleton equations, please either rewatch week 3's video or check out all the extra resources that I've posted for this week. I went through, scoured a lot of YouTube videos, and I found some awesome tutorials going through all of this stuff. And maybe they explain it better than I could. And that's okay. The important thing is that you learn how to do this. My first step is to identify the reactants in this equation and write those out. In this case, I have the reaction of solid copper and aqueous solution of silver 1 nitrate. Then it says to form, and when it says to form, that's my arrow. So that means that's what I would draw after the arrow. And that means that then my products are going to be aqueous copper 2 nitrate and solid silver. So I'm going to write these out. For the first part, I'm going to write out my reactants. When it says solid copper, well, that's easy. I just need to look at the element copper. Since it's not a compound, I don't need to worry about cross and drop or anything like that. Single elements, don't worry. The only time you need to worry about something is if it's Brinkelhoff, which copper is not. So I've got a solid copper and an aqueous solution of silver 1 nitrate. I'm going to write this on top so you can see that silver has a +1 charge. That's what the Roman numeral stands for. And then nitrate ends in ATE, so it's a polyatomic. If I look over here, I see nitrate is NO3 -1. So I can write that out, -1. Do your cross and drop. Don't just stare at it and try to figure it out. If you have not formed an X, you've done something wrong. So you should get AG1, which you don't need to put, NO3. And it tells you it's aqueous. Remember that the symbol for aqueous is AQ. And it forms aqueous copper 2 nitrate. So once again, I'm going to do my cross and drop. This time I'm going to do that for copper 2 nitrate. So I am going to erase this part here. And now I'm going to do it for copper. So copper 2 means that copper has a 2+ charge. And once again, nitrate, -1. We are going to cross and drop. And so we get CuNO3 2 plus solid silver. That's not a compound, so it's just Ag. Trying to leave a little bit of space here. Probably should have started a little closer to the left. Now that I've written this out, I can go back in and I can balance it. So now I need to count and see. I'm going to do this the long way first, but then I'm going to teach you guys a shortcut. So if you ever come across it, you'll know. Right now, I'm still going to count out my atoms. So I have copper, I have silver, I have nitrogen, and I have oxygen. Copper, I have 1, silver, I have 1, nitrogen, I have 1, but oxygen, I have 3 from this 3 subscript. Now I'm going to look at this. This 2 subscript on the outside, it's just like math. It's outside the parentheses, so it distributes to everything inside of this parentheses. So when I count this out, but it does not distribute to the copper because the copper is not inside the parentheses. So when I count this, once again, I have 1 copper, I have 1 silver, I'm going to keep them all together. I have 2 nitrogens now, and I have 6 oxygens. So it looks like my nitrogens and oxygens, which happen to be together because they're nitrates, are what I need to balance first. So I'm going to start by putting a 2 coefficient, and I'm actually just going to switch colors right now so that it's a little easier to see my coefficients. I'm going to put a 2 coefficient here, and when I do that, it distributes to everything. So I have 2 silvers now, I have 2 nitrogens, and I have 6 oxygens. Because once again, 3 and 2. Now I'm looking and it looks like copper's still balanced, which is good, but silver is no longer. Since I have 2 silvers on the left now, I need to add 2 silvers on the right. And I'm going to update that count and then, oh look, that actually balanced it out. So I have 1, 2, 1, 2. So if I were to ask myself, what is the mole to mole ratio between silver 1 nitrate and copper 2 nitrate? Right here, we see that for every 2 silver nitrates, we produce 1 copper nitrate, and that's it. So here are just some tips for balancing equations. I do want to stress that if you find you're struggling to balance something and it's taking a very, very, very long time, go back and double check your formulas first. Make sure that you formed the compounds correctly, because if you wrote the formulas out incorrectly, then it's going to be almost impossible to balance. If you know you've written out the formulas correctly, or it just gives you the skeleton equation, then begin looking at these other steps. So the first step is to always write the skeleton equation if it doesn't give it to you first. Do not forget your diatomic elements: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, Winkelhoff. Identify and count the number of atoms of each element for the reactants and the products. Balance the elements one at a time by using coefficients. Never, ever, ever change the subscripts. And a helpful hint, if you have lone elements like O2 or like silver, for instance, this should be a 2 subscript, by the way, not a big 2, but if you have like lone elements by themselves, save those to balance last, because those will be easy to figure out at the end. And then very last part, double check to make sure it's balanced, and then check that it's the lowest possible whole number ratio. So hopefully you guys are feeling okay about balancing equations. Remember, this is a trial and error process. There is no one set way. It all just comes with playing around with the coefficients. As you continue to practice, it will become easier and you'll begin to see more patterns. So the most important thing you can do to help is to practice. If you're still just completely confused and don't know what's going on, please check the extra resources that I've posted on Canvas this week. I have resources for everything we've covered so far that you need to be successful in this unit. Before I leave, I just wanted to show you guys a few memes that I thought were really funny. It's kind of like in place of the joke of the day. So I will let you guys pause this video and just take it all in. I relate to the one in the middle, and you will hear me say that to you guys a lot. So you have to be able to laugh at yourself, right? Just a reminder, for this week, make sure that you finish the balancing equations worksheet that you should have started as we were going through this video. Half of the problems were the ones that we did as practice. After you have finished the balancing equations worksheet, please watch the predicting products lesson and complete the second page with the predicting products worksheet. Then make sure that you submit both pages to Canvas in order to receive full credit for this week's lesson. Remember, I'm here if you guys need help. Lately, you guys have stopped coming to office hours, which half of me maybe thinks that means you understand it. But please don't be afraid to show up, even if it's just to say hi. I really miss you guys and I'd love to see your face. I really hope you guys are doing well, that you're staying safe and healthy. And just remember that I'm always here if you need anything. Take care, guys. Bye.